So to begin with, I'd like to start with a question and maybe a statement, and let's just see what we can do with that. So I'd like to consider tonight how it is that we can easily distinguish the origin of a musical sound, whether a plucking of a string, a blowing of a tube, a wind instrument, or in fact the human voice. How is it that all of those, when say played on the same musical pitch, can be so easily identified from one another, something that you know to be a fact? And let me just be a little more bold and provocative. In human language development, which certainly is an important part of our evolutionary process, we require the ability to rapidly and accurately distinguish one vowel sound from another. Now, before anyone accuses me of being anti-consonant, okay, I have nothing against consonants. It's just that they're mostly about sibilants and glottal stops and things that aren't very musical. And in fact, vowels are all about harmonic content and musical content, and that's why we'll be talking about that. Let me just also emphasize that I'll be taking a physicist's approach to this. Number one, I say that because you'll see the limits of my knowledge of neuroscience and biology, linguistics. I'm a physicist, not any of those things. But also I wanted to give you maybe just a little bit of insight into how a physicist might think about answering these kind of questions. What might be the first thing that you would do as a physicist to look into this? So how would we start? Well, let's start with something visual and something simple, something we can see. If we're going to be talking about sound and sound waves, you all know that that's something that's invisible, so physicists like models that we can see. You're going to see me plucking a spring, watching the pulse at 1/10 speed move down to the right and back to the left. I want to describe this wave as a transverse wave, a wave where the motion of the elements is up and down, the individual pieces of the spring go up and down, but the energy of the wave goes back and forth. Transverse, that would be the definition of transverse, okay? So let's play the clip. And watch carefully, watch the shape. Notice the shape stays pretty intact as we go from one end to the other and back. We spend a lot of time at the beginning of the course we teach in describing this motion, in learning about what causes speed, what causes propagation. Now watch two pulses, and as you watch them carefully, notice that they simply add up as they come together. They add up, they pass through one another, they add up, they pass through one another. The idea that's being shown here is a really important idea in physics, and it's the idea that I list here at the bottom called superposition, that the individual disturbances can add up together. And so these are some of the observations we can make. So if we move on now, so instead of just launching a single pulse, as I showed you, let me attempt to launch a pulse that will be periodic. That is to say, watch my hand. I wiggle, I send a pulse, it comes back, I send another pulse, it comes back. They all add up together in a certain way when all of a sudden, if I wiggle my fingers at just the right rate, note that I get this beautiful, sustained, simple motion, which we refer to as the fundamental vibration, the fundamental mode. In this case, 1 cycle, 1 repetition per second for this particular spring, okay? Now watch me as I continue to go slightly faster. I'm sending pulses, they're coming back, they're adding up. Not a lot of interesting things are happening until there's this very satisfying moment when finally, come on Majumder, you can get it. There we go. Okay, now see that beautiful shape that I've created by just wiggling? Look how little I have to put energy in to sustain this motion. A physicist would refer to this as resonance because small amount of energy in generates large amount of energy out. Okay, continue wiggling here. Just one more example of this. Watch me go a little bit faster. Waves come, they go. Again, not a lot of coherent motion. Eventually, though, you'll see I will achieve the next special shape of this. And that's what we call the third harmonic, and not surprisingly, not accidentally, it has 3 repetitions per second. 1, 2, 3. Simple pattern and simple ratio. Very good, thanks. Just to reiterate what you've just seen now, you've seen shapes that I can show here. Here's the fundamental at once times the frequency, twice times the frequency. For those physicists in the audience, you can see that the wavelength of this disturbance is getting shorter as we go down, just as the frequency is getting larger as we go down. The ratio is a simple mathematical relationship of 1 to 2 to 3. Only certain frequencies of wiggling generate these special patterns, which we call modes. Okay? Very important for the musical side of this. How do we generate these kinds of vibrations in musical instruments? We pluck them, we bow them, we strike them, we blow through them. And when that happens, instruments respond in this way. They respond by vibrating at their natural frequencies. And not just one, but in fact many modes can be excited simultaneously. What I showed you before was a way in which we could generate first the first one, then the second one, then the third one. But you should know that if I strike a generic instrument, it will respond in many of those simultaneously. What the frequency is depends on various physical properties. How big is it? Or how short is it? Is it made up of a tube of air? Or is it made up of a string? If it's a string, what's the tension in the string? Those kind of physical things are what determine the exact frequency. Okay? So now let's move on to a better model for what's actually happening for sound waves. Sound waves are waves, just as those I showed you, but they have a very important difference. So let's just start this video, and you'll see this is a slinky that's suspended from little strings. Can everyone see the difference in this motion? Okay, it's moving from left to right, and there are certain places where the spring is compressed and certain places where it's stretched out. Okay, this is a much better model for sound. We refer to this as a longitudinal wave because the motion of the elements is left and right in the same direction that the energy is moving, in this case from left to right in what's called a traveling wave. Everyone get that? So that's a longitudinal wave. Sound is this kind of a wave. That's why this is a nice way to look at it again as a physicist. You can't see sound waves, but this gives us a sense of what's happening. If you want to talk about sound, you need to make this translation. You need to change the slinky into air molecules. Okay? You need to think about the places where it's extra compressed as a small local increase in pressure over atmospheric pressure, and I mean small. Okay? If we change the local pressure by 10%, then that's fatal. Okay? I'm talking about changing local air pressure by parts in a billion to be audible, okay? And the speed of the wave, not what you see here, but more like hundreds of meters per second. So reaching your ears from my mouth in less than a tenth of a second, okay? So now here's my one-page translation from physics to music, okay? So first line, probably many people are familiar with. When a physicist talks about frequency, number of cycles or vibrations per second, or using our favorite unit, hertz, a hertz, cycles per second, a musician would talk about pitch. Now that's not exactly quite that simple, and we'll see in a moment what I mean by that. But here's almost a more important idea. Frequency ratios correspond to musical intervals. This is a really important part about how we hear music. When I go from that fundamental mode to the next mode, I've doubled the frequency. That's a ratio of 2 to 1, and we refer to that, musically speaking, as an octave. So if that first frequency happened to be 1 hertz and I went to 2 hertz, if we could hear that, that would sound like an octave. If I went from 100 hertz to 200 hertz, that's an octave. But if I go from 1,000 hertz to 2,000 hertz, it's a much bigger change, and yet we hear that as the identical musical interval, an octave. Okay? So we hear ratios as musical intervals. 3 to 2, another famous one called a perfect fifth. 4 to 3, a perfect fourth, etc. Those are the characteristic ratios that have been known about for a long time. And when I say a long time, I mean a long time. So our friend Pythagoras, 2,500 years ago, knew all about this and was really obsessed with the idea of the connection between mathematics and music, and did experiments slightly different than what I've shown you here, but actually quite similar, where he would take a string and pluck it, and would listen to that tone, and then would take the string and divide it in exactly half, and listen again, and notice that there's that octave interval. And oh, if I divide it instead of into halves, into 2/3 and 1/3, then I hear the difference between and there's that perfect fifth. Okay, so that's been known about for a long time. Okay, so last couple definitions before we jump into some examples. Pitch is not everything. Pitch is not everything. In fact, if it were, then my whole premise would be false. We wouldn't be able to tell apart one instrument from the other. So let me introduce this term called timbre. Maybe colloquially, a tone is a better idea, and it's not really a very good definition, but you see the idea here. Something besides the pitch and the loudness of the sound that allows us to identify one sound from another. Okay? In the next few minutes, hopefully you'll get a clue as to exactly what it is about the sound. Spectrum. This is the distribution of frequencies in this case that makes up the musical sound. And spectrum can be general, but here, as you've seen, I've already implied, we're talking about specific individual frequencies that correspond to these special modes of vibrations. So that's why I say discrete, certain specific frequencies in a ratio of 1 to 2 to 3. Okay? Good. So now moving ahead, let's start with the world's simplest tone that I could come up with. Here's a tuning fork, and I've chosen middle C as my favorite note for tonight. Okay, so here's a middle C, a tuning fork playing middle C. Let's all listen. Familiar sound. And there's something different and special about this musical sound compared to all others. Again, you want to think about that sound reaching your ears, going at 300 meters per second, those crests hitting your ear. And when we look, instead of our ear, if we use a microphone, which I did last week when I recorded this, what do we see? We see this very beautiful, very simple pressure variation that a microphone or your ear would hear. And again, how do we read this? Slightly above room pressure, slightly below room pressure, etc., up and down in a beautiful sinusoidal pattern. Okay? Now, what else can I tell you about this? A crest is reaching your ear every 3.9 milliseconds. Now, are you hearing every 3.9 milliseconds some sort of pulse of sound? No, that's way too fast for us to process. Instead, we hear it as a musical tone, as you just noticed. Okay? So now let me use some mathematics here, some little bit of fancy mathematics to turn this pressure as a function of time into something that's more about frequency. Okay? And if I look at the frequency spectrum of the sound, we see something not surprising. It's very pure. Look, it's a perfect 256 hertz tone, and that's it. That's all that's present in this sound. Okay? So that's a tuning fork, the simplest and most pure of all tones. Okay, so let me just give you a different one. Here's a little organ pipe tube. Let me blow it. Okay, so can folks sort of hear that that's middle C-ish as well, even if you don't have perfect pitch? You could sort of agree with that. Now, in here, you want to think about a compression wave just like that spring that was going up and down in its special mode that we saw before, except here, it's a compression wave of sound that's oscillating back and forth. Every time it reaches the end, a little bit leaks out, and that's what you're hearing with your ears. Okay? So that's the pattern that you want to think about. But here, let me just ask some rather obvious questions here. Is the pitch the same? Yeah, basically it is the same. Can you distinguish this sound from a tuning fork? Okay, yes again, obviously. Okay, so there must be something different about them. How could there not be something different if we can so easily distinguish them? Okay, and one other cool demonstration, remember when I wiggled faster on the spring, I achieved that next mode, which I said was twice the frequency of the first mode. Well, what happens if I do the equivalent for this tube by blowing extra hard into it? Well, let's listen. Everyone hear that? So we've gone an octave up simply by starting with that next mode. You can think of that shape in your head. Okay, so let's move on from there to my personal favorite. Okay? So let's find out something a little bit more interesting. So what I'm going to do is take my French horn and I'm going to play, hopefully, that same middle C. Okay, so once again, I think everyone would agree, yes, I can tell it was a French horn and not a tuning fork. Okay? But what is it about that French horn sound that's the same as the tuning fork, and what's different? That's what I want to get at. So let's have a look. That is what a microphone recorded last week when I played that note into the microphone. Okay, what is the same as the tuning fork? Well, you can see that the overall variation in number of repetitions per second is the same. It may be much more richer and more complicated, but in fact the overall periodic nature is the same. Okay, that's why we hear it as the same pitch. But when one looks to see what kind of frequencies are encoded in that, you realize that when I blow through my French horn, I don't just generate the fundamental mode, I generate many, many more. And that's what the spectrum looks like from my French horn. Okay? So check it out. Do we get the fundamental? Yes. Here's the second harmonic, twice, 3 times, 4 times, 5 times, and on and on and on. These notes up here are around the top of the piano. Okay? They're notes that are so high that you would say, well, how could those notes possibly be in there? You're playing a rather low, brass instrument, but they're all hidden inside. You don't hear them as separate notes. That's sort of one of the punchlines here. But they're part of the sound that makes up your identification process. Okay? Okay, so that's that. 2 quick audio demonstrations. I'm going to just ask for a little help again. Before we start this, I want to think about this idea of synthetic hearing. I want to convince you that our ear hears not individual notes when we generate all of these harmonics simultaneously, but one tone. So what you're going to hear is a certain familiar musical tone. You'll be able to identify it by the end, but we're going to build it up harmonic by harmonic. You're going to hear additional harmonics, first an octave and then a perfect fifth, slowly added on to the top. You're going to begin to just synthesize it into one sound, and then at the very end, hopefully, it'll be clear what it is. Thanks. Okay, only when the very last harmonic was played could you kind of get the idea that this was a plucked string, right? So that content, that very, very high harmonic content, that didn't affect our perception of the pitch, but it certainly did affect our perception of the tone and the quality of the sound. Is that clear? And could you hear, as I began to add in harmonics, for a moment you could hear a new note, but then it kind of blended together with the note before. So my next demonstration is similar. Here I want you to think of this complex tone that's made up of many harmonics as being kind of like a misty, shimmering mist where you can't pick out individual notes. But what I'm going to do for you is first with the fundamental and then with each harmonic, I'm going to turn on and off individual harmonics, and suddenly they sort of come out of the mist and make themselves known to you and then disappear back. So let's listen to this. So can everyone hear what I'm talking about? As I began to pulse them on and off, they certainly come out of the synthetic whole of the note and you identify them, but normally you wouldn't at all. Okay? So here we are with a little cross-section of the ear, so very rapid physiology lesson. Remember, I'm a physicist, so it's going to be extremely short, and this picture is too complicated for me, as you'll see in a moment. But nevertheless, here's a cross-section of the ear. The vibrations that hit the eardrum are transmitted to the inner ear via the bones of the middle ear, and all the magic happens in this remarkable organ called the cochlea, which is this little pea-shaped jelly roll well, okay, so, enough of that. I'm a physicist. Here's the physicist picture for the inner ear, okay? I've taken the jelly roll and I've unrolled it. You with me? Okay? So there's the jelly roll. Sound is coming in. There's fluid inside this inner ear. Here's a membrane called the basilar membrane that at this end is extremely stiff. At this end is extremely floppy. Okay? Sound comes in, and depending on the frequency of the waves, it sort of excites certain places along the basilar membrane. Hair cells all along the membrane then spatially map what regions of the basilar membrane are excited to tell the brain what frequency it is. And here's an amazing thing. The way this is mapped frequency-wise, it's about 8 octaves in 2.5 centimeters. Okay, that's the range of our hearing, roughly 8 octaves. Every 3 millimeters, and it's equally spaced octaves, right? So 10,000 hertz, 5,000 hertz, 2,500, 1,250, 625, like that, okay? That's the way it's mapped, so it should make you think of a little piano, right? Because that's exactly how a piano is mapped. Every octave is an equal distance on the piano, right? So maybe this helps us understand why it is we might hear intervals very similarly, regardless of whether it's doubling 2,000 to 4,000 or doubling 200 to 400, if you follow me. Okay, so that's a little bit about how the ear works. Remarkable things that you can share at your next dinner party. Okay, the ear is so sensitive that, as I said before, 1 part in a billion changes in atmospheric pressure. That's not even the limit of our hearing, but really middle of the hearing range. When that happens, molecules in these crests and troughs of the wave are moving by nanometers, that's right, nanometers of distance, while the molecules in this room are all the time moving at 300 meters per second, whizzing around the room, and yet the wave itself is this tiny displacement of air which we can hear without trouble. So it's absolutely remarkable. We can distinguish pitches that are extremely close together. 1 part in 1,000, our hearing system is able to distinguish those frequencies. And I'd just like to contrast that to how badly the ear does in sort of spatial sound analysis in contrast to the visual system. Think about the visual system, which is all about spatial analysis and actually really poor about frequency analysis, by which I mean color or wavelength, right? There's no way your visual system, you could argue, is as good as our hearing system in terms of its ability to distinguish. Okay, so to finish up here, let's just try a few vowel sounds. That was the sort of thing I started with. That was going to be the punchline. Here's my middle C. So what I recorded on a microphone last week was ooh, followed by ah, followed by e, all the same pitch, right? All middle C, or at least pretty close, right? And so let's look and see what the pressure variation for my oohs and ahs and e's looks like, okay? Ready? So there's the ooh. And you say, okay, that's okay, that's a periodic signal. It's a little bit odd shape, it's periodic, it repeats itself. There's the ah. More interesting, but can you see that there's something quite similar to the one above it? Right? I've lined them up carefully so that you can see that. And there's E. So somehow they all repeat every 3.9 milliseconds, right? That's the sense in which the pitch is the same. We hear the pitch as being the same because the fundamental frequency, the repetition period, is the same for all of them. But quite obviously, now you guys are experts, quite obviously the shape of the pressure variation is different, and we expect different frequency content. And what frequency content? We're talking about my vocal cords, then sort of amplified and altered by the presence of these cavities of my throat and my head and everything else. But let's look at them. So there's the Majumder ooh, okay? Fairly boring, you would now say, right? There's the fundamental, and there's the second harmonic and the third harmonic, and that's about all. Okay? There's the ah, where you see not only some frequencies down here, but then some higher frequencies. And then finally, there's the E. And again, I'd like to point out a couple of important facts. Look at the ah for a moment and notice that the fundamental frequency, the pitch that we interpret here, is not the loudest frequency present. Okay? Those frequencies are much louder, the second and third harmonic, but we still interpret this, the pitch, as being the fundamental pitch. Okay? Our brains are so used to hearing this series of 1, 2, 3, 4, and onward that we just naturally extrapolate back to 1 here. Okay? And I'd also like to point out that this sort of, there's a little bit of a wasteland here, and then all of a sudden, these very high frequency components emerge. And again, these are what you would think of for a soprano sort of range of voice, and that's because of these cavities here called vocal formants, which highlight and amplify certain parts of the spectrum. Okay, so then, to just end and summarize, could you have correctly identified which instrument or which vowel? Yes, I think you all could have. So there's obviously an ability to do that. We can even distinguish two individuals, probably a useful evolutionary tool, individuals speaking the same vowel sound. So I'm guessing that Professor Murphy, when he comes up, although he may have the same vocal range as me, that he's going to use some vowels, right? You plan to. and when he does, you will easily be able to tell the difference between his E and my E simply by subtle differences in the spectrum, not from the pitch. Okay. So for another day, other interesting things. We haven't talked about how the attack and decay of the sound affects sound identification. That's actually a really important fact, and I kind of haven't said much about it, how a sound turns on and turns off. Chords, multiple complex tones. Well, yeah, there's a lot more to music than just single pure tones that I played for you. 2D objects, like this one. Why is it that when I strike a lovely two-dimensional object, we hear that, and our brains desperately try to kind of make a pitch out of that, yeah? And you say, well, sort of, right? And that's because two-dimensional objects have much more complicated frequency patterns. They don't fall into this familiar 1 to 2 to 3 range. So our brains are trying to find a pitch there, but the different frequencies that are present don't fall into that pattern. And things like drum heads and other things make it more complicated. So I'm done, except I just couldn't end, I really couldn't end without homework, okay? So I'm sorry, I can't help myself, and you probably thought you were coming you wouldn't get homework, but you're getting homework, okay? So very simple, and I hope it's fun, and I hope it's interesting. It's a pretty cool demonstration. Find a piano, number 1. Open the top if you can. Hold down the sustain pedal, you raise up the felt, and you have then strings that can sympathetically vibrate when they hear sounds. Sing a vowel at a steady pitch into the piano. Literally get up there and sing into the piano an ah or an E or your favorite vowel. Stop, listen, And you should hear the piano singing, not just back to you, but singing the sound that's identifiably that vowel back to you. Try it with a few different vowels. It's really kind of a cool demonstration. And if you can understand each step in this process and then why the piano sounds like it does on its way back to you, you really will have gotten the message for tonight. Thank you very much.